Here's a quick lesson on phase diagrams, how to read those. They're pretty easy to read once you get the hang of them. So here we go. Phase diagrams, they are a graph of temperature versus pressure. Normally when we think of phase changes, we only think of temperature, or at least that's what we thought of up until now. But with phase diagrams, they bring in that added dimension of pressure because pressure can affect the states of matter. Lines on the phase diagram indicate where a phase change is going on. So, phase diagrams are Y-shaped curves. This is the phase diagram for water. They always look kind of like a Y. Now, it may be a skinnier Y or a wider Y. It may be leaning one way or another, but they're always shaped like a Y. When you go to label the states of matter, it always goes like this. Solid on this side of the Y, on the left side. Liquid is always in the middle of that Y, and gas is on the right side of the Y, or vapor. We can put that there as well. Okay, now, the lines indicate where there are phase changes. So if we're talking about something going across this line that I'm highlighting in red, going across solid to liquid, then that is where you're going to find your melting point. If we're going the other way, liquid to solid, then this is where you're also going to find your freezing point. So they are the changes in the phases. So going across the lines, they connect all conditions of temperature and pressure where equilibrium exists between the phases on either side of the line. So, again, on this line that I'm highlighting in red, anywhere along this line are the conditions of pressure and temperature where you have equilibrium. So you have solid and liquid going in equilibrium along that line, and that is where your phase changes occur. All right, so if we go from solid to liquid, that's melting. Going across the line, let's say we pick a pressure and then we're increasing the temperature, and we go across the liquid gas line, that's going to be vaporization, or your boiling points are going to be found along that line. Coming down on the other side, let's say we've picked a pressure that's pretty low and we're going to decrease temperature, so coming across the gas solid line, and that's called deposition. The gas is going to deposit a solid on a substance, so that's deposition. Now going the other way, across that same line, solid to gas, that is sublimation. So you pick a pressure and increase the temperature, and you have sublimation going on. Going the other way, from gas to liquid, that's where you have condensation. And if we have a particular pressure and we're decreasing the temperature and go across the solid liquid line, that is freezing. Okay. Your two other major points that you have on a phase diagram, your triple point. Your triple point is the junction of the Y. The triple point is where all three phases exist in equilibrium. It has to be in equilibrium, and at this point, right here at this juncture, you have, for water, boiling ice water, and you never run out of ice, you never run out of water, and you never run out of steam. It is just in equilibrium. They're all forming each other as it goes along. Okay, the other major point that you're going to find is the critical point. Really, what's important about the critical point is the critical temperature. So that is the temperature that corresponds to that critical point. So down here somewhere. You can also have a critical pressure, but that's not as important. The critical temperature is the temperature at which the liquid can no longer or the substance can no longer exist as a liquid. No matter how much pressure you put on it, the molecules are just moving too fast. They will not succumb to their attractive forces. Now, I'm going to back that up again. We go from the phase diagram of water, watch the shape of the curve, and we're going to go to a phase diagram of carbon dioxide. Notice that the solid-liquid line has changed, and it's going to tell us comparative density. It's leaning the other way. Line angled right, so the solid is more dense than the liquid. Also, if we just pick a pressure, and let's pick normal pressure, 1 atmosphere, and we go, as we increase the temperature, carbon dioxide is not going to enter the liquid phase. It, as you increase temperature, crosses the solid gas line, so it actually, as you increase temperature, will sublime, and that's dry ice. It has that fog. All right. Then we go back to water. Notice that that solid liquid line is leaning to the left, and left, lean, liquid is more dense. This is really with water, but you can tell the density of solid and liquid based on the angle of that line. All right, now, normal freezing point. When they say things are normal, that means it is at standard pressure. Standard pressure is 1 atmosphere, or 760 millimeters of mercury, or 101.3 kilopascals. One of those is going to be normal. They're all equal to one another. So what you would do is you would go across here. If we're looking at normal freezing point, you want to go across, find the freezing point, solid and liquid line, and then you go down to temperature. And for water, that's going to correspond to 0 degrees C. Now, if we're talking about normal boiling point, again, you deal with 1 atmosphere pressure or standard pressure, and you're going to go all the way over here to the liquid gas line, because that's where boiling happens. And then go down, and that's going to tell you your normal boiling point. It's 100 degrees C. Triple point for water, just interesting little facts. It's just above no pressure, so just above a vacuum, and just above the freezing point of water. And that's where you would have boiling ice water, and all of those would exist in equilibrium. Critical point for water is 374 degrees Celsius, so that's pretty hot. Above that temperature, water can no longer exist as a liquid.